So when we charge a capacitor with constant current, what would be the voltage? It would be a straight line. Do you know why? Just intuitively why? If you think about constant current, it means that you load the amount of the area to load the charge of the capacitor is constant. And the voltage, right, is the Q divided by C, so the voltage keeps going up. It means that you linearly load charge in your device. So the output will look like this straight line. Right? A very interesting thing is that if you look at this equation, constant current means that the current at CL can go out, so you only have to integrate the out. So there's nothing else but the out2 minus the out1. Right? It's the easiest way to calculate the integral. And the delay, right, go to 0 to 5 is when you reach the out1 is 0, the out2 is what? 1F, the DDF. So you can calculate the delay, right, as this current IP, with no ion, CL divided over F divided 2IP. And in the case we use our transistor, the model with IDSAT or ion, whatever you want to call it, then we need not to calculate the delay, even simpler. Right? So by the end of the day, when we do our calculation, like the project, we use this formula, use the RF model or the AF model. The RF model is recorded in the IDSAT or if there is a channel modulation table, it will be one of these two formula. If there is constant current, it will be this formula. The question is, what value used for that current? Right? It's constant, but which value? Right? So, before we go, let's go back to the other slides. I didn't put them back here, but we make thinking. So if we consider this one, we are along this curve, right? So a good way to use constant current would be an average value here in the middle, right? Something like that. So we start with higher current, it goes with lower current, but something there in the middle will be okay. Oh yeah, this one is a little bit more difficult. I need to find a better way to calculate, which is one of the things that I'm saying. And in this one, again, but it's not a realistic case compare. This one here is a little more complex. But we know that in this case, the transit going to stop when you reach almost VDDF. So we kind of need to calculate the average of the current through this curve. It's like we have to take an integral. Let's see if we can do a simpler way. It would be the average of the current. You see here the current is more, bigger. But guess what? It's never ion. So the simplest method you could use here is to use ion. When you go simply, if you use ion, you will get the propagation delay that is much smaller than a realistic one. Right? So not good idea to use ion. So the technology keep giving you ion, it doesn't matter. What really matters is the current that goes from 0 to the middle point. So let's now see if we can get a good model for the current, for the realistic case. There are a few things here, but after that, let me see. So you remember this plot that we showed before, right? So we saw that, because the input start varying, the output start varying, it's not a step function, and the output start varying during, right? We need to calculate the 50% of the input to the 50% of the output, which is not an exact distance. So how do we calculate that? Right? So first of all, we look intuitively how they're happening in this plot. Charge here. So we start from VDD, let's say we are at a certain point of the inverter, and then when we reach VDDF, we are done. get used to the paper. Because normally, to really use paper, you probably need to do a lot of work. It takes training to read paper and get used to understand the content. Me, myself, I still get confused and I understand what I'm talking about. So it's a good practice. Especially because if you work in this community, there are people that come from all over the world, they learn their English in schools, sometimes by themselves, sometimes they write in their language, with English word. So it's very important to be able to understand whatever it is in the paper. The content is important. Of course, it's beautifully written, it's nice to read, but you still want to not throw away paper that has good information just because the person is writing in English. Thank you. So this is kind of what the paper is doing. Right? So again, this exploit of the characteristic is the discharge through the NMOS, right? So this doing that curve here. Does anyone does not understand because of why we have this great curve? Because while the input is changing, the output is changing. You cannot get the smooth characteristic. Interesting enough, we normally reach the top, we assume that we reach the top when the output is already halfway. So the maximum current we get is almost at the end of the next. You know, this is only flip-flop curve, but there are the other curves in the middle, right? Correspond to other VGS varies continuously. It's not this step. This is just to give you an idea. But the point is, we never use ion. We use a much lower case. So first of all, we need this current will be the important one. So for sure it's not ion that we use in that formula. That's why I have the formula again. Autopropagation. Delay equal CLVD 2IF. That's the current we want to calculate. Alright, we saw ion. We know ion is wrong. Because we always work with this guy here all the time, from here to here. I see one thing, two things. First of all, we never raise the value. And one, we start from much lower current. Right? The other thing we also see that there is almost no guarantee that actually VGS is equal to VDD because VDD is the one we talk. We have some kind of square collinear, so the VTD F would be very low in this plot. Right? So until we really reach that F value, there's not really much charge on the output. So anyway, so what we really care in the curve is going from here, which is actually in the case of the definition of propagation delay is from when the input is VDDF to the output is VDDF, right? So it starts from here and it finishes here, right? So the real curve we will have to use is this discharge trajectory, right? But why we don't try to approximate with a straight line like the red one, right? In this way, we can just write down a very simple equation between VDD and the current. The other thing, right? So that's, we assume we come from this trajectory. The other thing is that it's still difficult because we still have to look at all these currents, right? Current here, current here, current here, current here. And you see the slopes, right, is not equal for all the curves. Right? So changing, there are different channel combinations for different kind of equalizers. So the second trick we do is to linearize on the curve to have all the same slope. So we have two approximations. First approximation is that making the curve as a straight line. The second approximation thinks that all the ID of a validity curve are actually parallel, infinite parallel lines. So they're all with the same slope. So those are the two approximations, which are not too bad of approximation to the plot. So why we do those approximations? Of course, approximation, we find out, basically, you know, we saw the integral before, the time to be calculated, and the time it takes to go, you see this, make an average of this time to go from when VGS is equal to VDF, the input to the output VDF. So that's how you define the integral. The problem is that the integral, you see, it has this dependency of VDS and VGS inside the equation. So this is actually not a unidimensional integral. You can do it as a two-dimensional integral, Stokes theorem, or it's a path integral. And it will be actually a path integral, so this curve here, hard to solve. But if you make a dependency between VGS and VDS to this red line, in the paper you find out empirically they can be approximated by this. Just going in the plot, find out there can be this dependency. So now there is a straight dependency between VDS and VGS. VGS equal 1/2 VDS, something like that. So anyway, you plug into, I think this is VDD. But, you know, it's true, I didn't do the calculation, but the point is, by approximating the relation between VGS and VDS with this equation, and using this approximation, linear approximation of the current, you know, we plug now this inside the integral we get like a regular integral, you solve the integral, and interesting enough, you get this equation. CL VDD divided 2 IH minus IL, where IH and IL they are missing, no, they are defined here. H is the top current of this one is the initial current is the level 1, and H is the top one. So you find out actually is this equation that you can write down. You can, if you define IF as the average between these two currents, you get the same formula. Interesting enough. So again, with this full approximation, a lot of calculation, we find out that what we have to put here, you can use the formula, the constant current. We just need to put the average between the current and the stop point, which is for VGS equal to VDD, and VDS equal to VDDF. It's called the H current. And the current for VGS equal to VDDF, and VDS equal to VDD, which is this one. We average those two currents, we get our effective current. So, it's no concept. At the end of the day, the only thing you need to remember is this average effective current. So that's your model for the effective current. So, lot of concept, but very simple results. So that's why this guy went through all this code. It probably, how they come up with such an easy formula, such something so complicated, because they try an approximation at the time, they made a calculation, till they come to a calculation that was very easy. Right? That's okay. These are the good approximations. Then they tried the model and they looked, it was working fine, and then you get the figure. So it's probably a lot of trial and error, a lot of experience. Remember, I think this guy from IBM when IBM was on the top company working this stuff. What's that?
How did that approximation for ID? Here it is like
Yes.
VM
Oh, this is basically these are like just showing this GM into 0 by the approximation that makes linear curve. So the fact that you see, if you look at G0, it means there is 97 is this point, and then there is maybe I confused VDS minus VDG, maybe the sign goes. I have to tell you one thing, it's important. It's not uniform. Some people call the ID set the value that is at the VD set. Some people call ID set what I call ion. So most likely then they used to be called ID set the maximum current. So I have the minus, so the formula is not identical. I didn't change it because of only this data. You'll find out sometime ID set is this point here. Actually not even here, this point here. This is now ID set is the maximum current. So basically, you can, it's a convention, right? Some people call, so you have one, and then you create from this set on, you use this, plus one ADS, and the other one to be ID set, one minus lambda, so VDD minus VDS. So when this is maximum, then you get the whole other set. Then it goes down. Unfortunately, they are both used in literature. Because a set means saturation. So one can use ID set O is the volume of the transistor. When the transistor reaches saturation, and the other can be saturation because it's the biggest you can get. The saturation is used in a different meaning, right? In different context. They both exist. But when we do the project, we make it very explicit. So you don't get confused. Conceptually it's the same. Just be sure that if you look to a set of technology, you look to the plot, you have to see what they mean by the set.
बस कर दे
Fortunately,
बोलूँ बस कर
some
दे
people they take from other paper and they said it's the only one I use in my I hope you get confused. Try to remember constant one. You could actually make more uniform, but then you read the paper and it's different and you're like, oh, I understand. Just be kind of flexible and stuff. I still get confused too. I do check the number of your question twice. They usually now is doing that.
पढ़ाता बहुत अच्छा है ये भाई पढ़ाता बहुत अच्छा है रियलिस्टिक चीज़ें
But
पढ़ाता है
the real point is like this. Delay is, if you want to be very, very optimistic, use ID set or ion, which is, or ID set in the other definition. Or, in reality, we do the curve. Simply is never there. It's actually spending enough time there between those two curves. So using the effective current, find like this is a good approximation. So IH and IL. So normally, let's say your circuit, you know that you're on the maximum current, or it's whatever, like you do, and then you give the channel population, and then the lamp is let's go, you have to calculate yourself the IH. And another way you can calculate the AF. Because if you know that, let's say it's linear, with the big threshold voltage, the equation that resistor you use that the approximation by that as well. We'll try to make some example of those calculations. And again, this is not a completed example, it's a project. Project is like work. So I purposely don't give you all the information. You need to search in the slide and try to be creative. Because that's, I want to try to recreate a real life condition for you. And the value of the project is really to understand what you did and be able to explain it. So having a wrong solution is a very good project. I'm not reaching to the exact solution, I'm reaching to you understanding and trying to explain how you got there. So that's the value of the project. So you can copy knowledge from another person, and you cannot explain it, you just memorize it, you're not memorize the exam. So for me, it's much the value that you really put into it. You try to use, Excel, or maybe use MATLAB, or use Python, or maybe just do hand calculation. It's up to you. I've seen all of that happen, and they're all actually pretty excellent. And of course, for power consumption. It's not, because the memory, you only read one register of the full memory at a time. Power consumption of the memory is inexistent. But the person student was good, tried to explain how to calculate, and then I get to put in, then we took debate. So that's what this is all about. Me is only even experience of engineering work. I'm gonna do another couple of slides and then we
बस करते हैं
finish a little early today. Okay?
ये तो सीरियस हो गया
You know, you can, this is another paper from other people, Yoshida and Bornani. They think like suggested to me. Again, you don't have to read all the paper, okay? You get the concept. You know, and from this paper, they provide an interesting consideration. This is very similar. It shows that actually the curve, new technology is not really doing like this, it's even worse. It's more kind of like this one that goes down here. So even if you use their age, you're very optimistic. It's even lower than that. So the ion itself, you see this guy called this ion, or we could call ion as the IESET max. Everybody call it like some different way. It's just when everything is really deep. Right? Not correct. We decide to use this average here. Effective current. It does something else, is to define a characteristic current, and you know, and is to do that, and then it goes through all that, and you find out that the current is more something that is close to here. It varies now. I don't really understand really why, but that's it. So there, what I'm going to say, there are different methodologies. Also, when you have stack devices like net gate, you have 3 inputs, then you find out that this is not true anymore, so you have to use a third current. So there are people that come up even more sophisticated model to come up calculate the effective current. But the good thing is that once you have the effective current, like the effective resistance, you remember the formula of effective resistance? No, it's like 3/4, you know, VDD divided by any set. You know, and then multiply by logarithm 2, divide by logarithm 2. So you can always get it from there in the CL. Same thing here. So the question is to come up always with a very simple way to calculate this effective current, and get to that. So this other one here, you found out, it's my last slide for today. You find out that there is this concept called DIGO. In the new technology, short channel, non-channel modulation, we have this problem of when you change the voltage of the drain, you actually change the threshold of the device. It's a little bit different, but the effect is always to get this low. It's much more pronounced, right? So in this case, you see this problem use anti-sat for this current. But the interesting thing is that the modulation worsens the device. So thinner is the device, what happens? You get more needle effect, and your high current goes down. So that's why when you go to the changing the technology after the Leonard's law, you start getting this effect called the Dibble, you get this kind of curve. And guess what? You make the device theoretically more conductive. The effective current is fast, and that's why we can get fast. That's why we get one of the reasons why we get fast. So that's one of the problems because of the Dibble effect. So I was just want to show you, I was telling you last week how the technology should be why this problem. The Dibble is one of those. So everyone in the day want to questions. I think this is like changed completely here, so I think it's a good place to stop. Yeah, it's going to be more. I couldn't start, but I think we have enough material for her. Before you go, at the end of the lesson, I they decided not to split the last one, they decided to raise light per copy, because I think it's easier for you to study. Last year was divided somewhere, I think that was right. The total divided, I think that was. Let's go to this last, yeah, there will be two required readings. One is actually for the last one tomorrow, so it doesn't matter, it was an handout from Professor Stanford. This one is model of the guy. Required reading again, I want to memorize the paper and go through the math calculation. Understanding how the approach is being used properly as well. And they've asked that